Let's investigate our conical pendulum in a little bit more detail. So there you go. So as it goes around in the circle, it's a horizontal circle, but when you take into account the string, it forms a cone. And the idea being it was going around with a constant angular velocity. So I'll give the cone some dimensions. We've got a height, a radius, an angle the string makes with the vertical. Now, so when we're going to solve these problems, draw yourself a force diagram, because that's what we're interested in. The helicopter is, if you like, Bob. So the force is acting on it. It's connected by a string. So there's going to be tension going up the string. So as I was saying the other day, always away from the object. So there's a force. And there's the force due to gravity. That's it. That's it for this little problem. Theta was the angle it makes, our angular velocity. So okay, we resolve them, but again we're going to break it into horizontal and vertical because it's a lot easier to deal with. Because horizontally, it's just circular motion. So we know the resultant force is circular motion, mr omega squared or mv squared on r, depending on how we want to deal with the velocity. So vertically, nothing, because hopefully it's staying in a nice horizontal circle. Now that might change. If I speed it up, what happens to the helicopter? Yeah, it lifts. So the radius becomes bigger and the helicopter goes higher. So all my horizontal forces will equal mv squared on r. And all my vertical forces will equal 0. Okay. So my force diagram, well, tension is not horizontal or vertical, so we broke it up into its two components, or its two vectors, whatever you want to call them. We need to identify where theta is, so we can work out whether it's going to be cos theta or sine theta. So horizontally, well, horizontally is opposite the theta, so it'll be sine theta component. So T sine theta horizontally, and gravity is totally vertical. So that's all there is horizontally. So I know that the T sine theta must be that centripetal force mv squared on r, or mr omega squared if we're using angular velocity. Vertically, there we go, we've got the component of tension going up, so that'll be T cos theta, because the vertical, you'll notice, is adjacent to the theta, and mg going down. So T cos theta minus mg, because they're in opposite directions, but they'll sum to equal 0, meaning that they equal each other. So we've got a couple of equations that we can play around with. I can eliminate the tension by writing sine over cos, which of course is tan theta. And so I come up with an expression like this. So tan theta will be v squared on rg. If I was dealing with angular velocity, I'd end up with r omega squared on g. But if we go back to our triangle, that tan theta is radius on height. So I can substitute that in, and we get v squared on rg is r on h. So the height of the pendulum, which basically was how far below, what you call that, the peak of the cone, if you like, where I was holding the string, how far below is h. So that's what we're saying. If you speed up velocity, that means the denominator is getting bigger, which means the height is getting smaller, and that's why the helicopter goes up, the height below the central position. G on omega squared, I suppose, if you do it in angular velocity, it's even more obvious why when you increase angular velocity it goes up, because gravity, of course, we're assuming constant. So some implications. So as I was saying, the depth of the pendulum is actually independent of the length of the string. The length of the string is irrelevant. Other than, obviously, it couldn't be further down than the length of the string. That would be a bit hard. And as the speed increases, Bob will rise. So yes, you could get a question like this. If we increase the number of revolutions per minute from 60 to 90, how far up will Bob rise? So I'd started off the same. Draw my force diagram. There's my string with tension, gravity going down, and I'll just put in some dimensions there so I can resolve tension and other things. So horizontal force is mv squared on r. By the way, if they say draw a force diagram, you don't draw in height and radius. They're obviously not forces. And vertical forces are 0. So pretty much the same as I just did. T sine theta I'm using angular velocity for this one because they're talking about revolutions per minute. So mr omega squared, t cos theta, and we get mg. So again, exactly what I just did. Tan theta becomes r omega squared on g. We know tan theta is radius on height. I've got a formula for height. So basically it's just a matter of subbing in. We're at 60 revolutions per minute, but we need it to be in radians per second. So that's 2 pi radians per second. The height of my bob is g on 4 pi squared. When it's 90 revolutions per minute, it turns out to be g on 9 pi. So how far has it risen? Well, it's just the difference between the two. That's not that bad. I mean, you just need to get that little formula and you work it out quite easily. So 0.14 of a metre. Here's one from an HSC, 2002. There's an interesting one in that the conical pendulum is resting on a cone. So there's sort of like 2 cones happening in this problem. So you get the problem that cone there is actually a surface that the bob's on. Oh. So we've got a string and it's rotating around. That's why you'll notice another force there. Yeah. There's a normal force. Whenever you have connection with a surface, you'll have a normal force at right angles to the surface. So that's that extra force of N there. Okay. What else do we need to know in this problem? They've told us about tension and the gravitational force as well. Okay, with the aid of a diagram, because we know how you love to draw diagrams, so they're specifically said, with the aid of a diagram, we're going to show that the vertical component of that normal force is n sine alpha. So let's draw up our forces. Tension going up the string. Now we'll resolve that, and alpha is down in that location there. There's also normal force. Now, where is alpha? Let's just go back to the original problem. Remember, the bob is sitting on the cone. It's said that that angle there was alpha. I've got to find out where alpha is going to be in this triangle there. But we know the normal force is at right angles. So what can we do? Well, we've got alternate angles there, so that must be alpha, which means the one inside must be 90 minus alpha, which means alpha must be the angle at the top there. So we can get alpha into our triangle. So all right, now I can look at it and see what the vertical component, the vertical one is opposite n, so it should be n sine alpha. Of course, gravity is in there as well. Just to, I don't want to just write down n sine alpha because it doesn't look like I've answered the question. So I've labelled that vector C for component. And I can say, oh look, C over n is sine alpha, so that component is n sine alpha. That's the first part of the problem. We're now going to show that the tension force and the normal force add together to give mg on sine alpha, and then they want us to find an expression for the tension force minus the normal force, and they want it in terms of the mass, the length of the string, and the angular velocity. Okay. Horizontal forces, I'm going to use angular velocity because I notice they mention angular velocity in their answer here. So horizontally we have, there's a component of tension going to the left, but there's also a component of the normal force going to the right. And both of them are cosine because they're both adjacent horizontally. They will sum together. Now, how do I know which one to make positive? Remember, the resultant force for circular motion is always directed towards the centre. So that would be to the left in our diagram. So that will be the positive direction. Okay, vertical forces. Component of tension, component normal, and gravitational force. They all add together to give 0. Because they add together to give 0, it doesn't really matter which one I make positive, which one I make negative. But I can rewrite that to make t sine alpha plus n sine alpha equal to mg. So we're looking for t plus n. Okay, well, t sine alpha plus n sine alpha is mg. I'll just divide by sine alpha. Okay. They then said find a similar expression, t minus n So I'll get mr omega squared on cos alpha, but they wanted it in terms of, what was it? Mass, length of the string, and angular velocity. I've got mass, I've got angular velocity, I haven't got length of the string, but I've got r over cos alpha. Now, if you go back to the diagram, the length of the string, so the radius over the length of the string would be cos alpha. So the length of the string is r on cos alpha, so we get ml omega squared. We're going to increase the angular velocity until the normal force is equal to 0. That'll be the instant that it comes off the cone. As soon as it's no longer in contact, there is no normal force. So we're increasing it until that happens. Final expression for that value in terms of alpha, the length of the string, and gravity. So we now know n is equal to 0 for our problem. So tension, mg on sine alpha, according to my left-hand equation. On my right-hand equation, tension would be ml omega squared. Well, it's the same value. So I'll just equate the two, and we want to make omega the subject. So mg on sine alpha is ml omega squared. We can divide through by mass. Omega squared is g on L sine alpha, and there we have an expression in terms of alpha, L, and gravity. So it'll be the square root of g on L sine alpha. All right, time to play.